We can use the concept of KSP to decide if a precipitate will form when two different aqueous solutions are mixed together. Imagine that we were to mix together two aqueous solutions, one of calcium chloride and one of sodium fluoride. We can use double replacement first in order to predict what our products would be. We would have sodium chloride, that would be one product, and we would have calcium fluoride, which would be the other product. We could then balance the equation as well. We would need a coefficient of 2 out in front of the sodium chloride, and we would also need a coefficient of 2 out in front of the sodium fluoride reactant. Then we would normally look at our solubility rules and decide what the states of matter are of our products. This is what we would have learned last semester. Sodium chloride would be aqueous because both of those ions would create a salt that's soluble. And our calcium fluoride, you will actually find that on your KSP chart. And so that one is very insoluble due to the calcium ion, and it actually will be a solid precipitate that would form. So if a precipitate is going to form when we mix those two solutions together, the possibility would be that it would be calcium fluoride, since the sodium fluoride would be soluble in pretty much all proportions. Our calcium fluoride then, we could write our dissociation equation for. The solid calcium fluoride would break up into calcium ions to a small extent and 2 moles of fluoride ions to a small extent. The thing is, depending on the concentrations of our reactants that we mix together, the calcium chloride and the sodium fluoride, we might not actually form a precipitate. So we have to decide if it's going to actually occur, and that's going to be done by using something called the ion product. When we write our equilibrium expression, we normally set it equal to the KSP. But if we have non-equilibrium concentrations in the mass action expression, we call it the ion product. So we would have the concentration of our calcium ions times the concentration of our fluoride ions squared, and we would set that equal to the IP, or ion product for short. And a few different situations could happen when we calculate that ion product with non-equilibrium concentrations. If the ion product is greater than the KSP, then a precipitate will occur. The solution would be supersaturated. If the ion product is exactly equal to the KSP, the solution would be in equilibrium at that point. It would be saturated. If the ion product is less than the KSP, a precipitate would not occur, and we would say the solution is unsaturated. So we're only going to actually get that calcium fluoride precipitate if we have a situation where the ion product is greater than the KSP value for calcium fluoride. So let's try an example to figure out if we will actually get a precipitate. Will a precipitate form when 0.15 liters of 0.1 molar lead-2 nitrate and 0.1 liters of 0.2 molar sodium chloride are mixed? So first we want to write our overall equation and figure out what that precipitate would even be in the first place if we were going to have one. So our two reactants are the lead-2 nitrate and the sodium chloride. So this goes back to what we learned last semester about writing balanced equations and predicting products. We're going to start with our lead-2 nitrate, PbNO3 and that would be aqueous, plus we're going to have our aqueous sodium chloride solution that we're mixing with that. When we predict our products, we're going to have a double replacement reaction. We will form sodium nitrate, and that would end up being aqueous according to the solubility rules, plus our other product would be lead chloride, and the formula would be PbCl2, and that would be a soluble or a solid according to our solubility rules, so it's going to be the possible precipitate that we would form. You also will find lead-2 chloride written on that KSP chart as well, so that's another hint that that would be the precipitate that's possible. Next, we will balance our equation. We are going to need a 2 out in front of our NaCl, and we would have a 2 out in front of our sodium nitrate. Since the lead chloride is the possible precipitate that we could form, we're going to start there now and write our dissociation equation for that slightly soluble salt. So we would have solid lead-2 chloride breaking up into lead ions and 2 moles of chloride ions. Our KSP for this process, we're going to have to look that up because we're going to have to make a comparison at the end. That's equal to 1.7 times 10 to the negative fifth. And for now, what we want to find is we want to find the ion product. That ion product will be equal to essentially the equilibrium expression, the same one we would write for the KSP. We would have the concentration of the lead ions times the concentration of the chloride ions squared. So in order to find the ion product, we have to determine what those concentrations are and then plug them in. Once we plug them in, we can compare that ion product value to our known KSP value and see if a precipitate will actually form. A precipitate will form only if that ion product is greater than the KSP value. So that's what we're going to end up checking out to find. We have to do a little bit of stoichiometry and calculations in order to figure out what the lead concentration is and what the chloride concentration is. So remember, we have to plug molarity into those brackets. So we have to calculate the molarities of both of those. So we can start with our lead concentration. And we want to figure out what the concentration is after we mix these two solutions together. So even though the problem tells us that it was 0.1 molar initially, that's the molarity when it was in its own separate flask. So we need to get that new concentration now. So starting with calculating our concentration, we're going to take our initial 0.1 moles of our lead ion per liter times our volume in liters, which was 0.150 liters. That would just be over 1. Our liters would cancel, and our number of moles of lead is 0.015 moles. To get our molarity, we now have to take those moles and divide by the total volume of the solution in liters. So we're going to divide by our total volume, which is 0.250 liters. This gives us a lead concentration of 0.060 molar. So we'll make a note of that for now, and that's going to be what goes into our concentration for our lead ions when we calculate our ion product. Next, we want to calculate the concentration of our chloride ions in this new solution. To calculate the concentration of chloride ions, we're going to take the molarity of sodium chloride, which is where the chloride ions came from, which is 0.2 moles of chloride ions per liter, multiply by the volume of that solution to get the number of moles, 0.100 liters. Our liters will cancel, and that will give us 0.020 moles of chloride ions. To get the new molarity, we take the moles of chloride ions and we divide by the total volume in liters. So we will divide by 0.250 liters. This gives us a molarity of 0.080 molar for the chloride ions. Next, we want to calculate the ion product. The ion product is equal to the concentration of lead ions in solution times the concentration of chloride ions in solution squared. So now we can plug in those values. Our lead molarity we got was 0.06 molar. The chloride concentration was 0.08 molar, and that'll be squared. This gives us an ion product of 3.8 times 10 to the negative fourth. Our KSP off of the chart for our lead 2 chloride was 1.7 times 10 to the negative fifth. So in this example, our ion product was greater than our KSP for lead 2 chloride. Therefore, this means that a precipitate will form. Let's try another example. Will a precipitate form if 50 milliliters of 0.0010 molar calcium chloride and 50 milliliters of 0.010 molar sodium sulfate are mixed? First, let's write our overall reaction. We have calcium chloride plus sodium sulfate. And so our products are going to be sodium chloride, which will be aqueous, plus we're going to have calcium sulfate. Calcium sulfate would end up being a solid. So if we're going to form a precipitate at all, it would be the calcium sulfate because according to the solubility rules, that would be insoluble. So that's going to be our possible precipitate that we would form. So we want to write the dissociation of our solid calcium sulfate into its ions. We'll have aqueous calcium ions plus sulfate ions. The KSP for this dissociation is equal to 2.4 times 10 to the negative fifth. We're going to want to figure out what the ion product is, and that would be the concentration of calcium ions times the concentration of sulfate ions. To calculate the ion product, first let's start by getting the concentration of calcium ions in our new solution. So calcium ions all would have came from our solution of calcium chloride. That's where all the calcium ions were located. So we want to take the molarity of that solution. It was 0.0010 molar, so that many moles of calcium per liter, and multiply by the volume in liters, so times 0.050 liters. Here our liters will cancel, and our number of moles of calcium ions is 5 times 10 to the negative fifth. To get the concentration, we now have to divide by the total volume in liters. So we had 50 milliliters of one solution and 50 milliliters of another. We have a total of 100 milliliters. So we're going to divide by 0.100 liters to get the concentration. So our calcium ion concentration in our new solution comes out to being 5 times 10 to the negative fourth molar. Next, we'll calculate the concentration of sulfate ions in solution. Sulfate ions are all going to come from the sodium sulfate. So we're going to start with our molarity of sodium sulfate, 0.010 moles of sulfate ions per liter, times the volume in liters. We had 50 milliliters of that solution. So multiplying by 0.050 liters, that's essentially over 1. Our liters will cancel, and that gives us 5 times 10 to the negative fourth moles of our sulfate ions. We want to get molarity, so now we're going to divide by our total volume in liters, which we said was 100 milliliters, so we'll divide by 0.100 liters. This gives us a concentration for our sulfate ions of being 5 times 10 to the negative third molar. Next, we're going to plug those concentrations into our ion product expression. So we had concentration of calcium ions times concentration of sulfate ions. Our calcium ion concentration came out to being 5 times 10 to the negative fourth molar times our sulfate ion concentration, which was 5 times 10 to the negative third molar. This gives us an ion product of 2.5 times 10 to the negative sixth. Our KSP value for calcium sulfate was 2.4 times 10 to the negative fifth. So in this example, when we compare our ion product to our KSP, the ion product value is less than the KSP. Therefore, no precipitate will be formed. The ion product has to exceed the KSP value for there actually to be a precipitate. And in this case, we had 10 to the negative sixth, which is smaller than 10 to the negative fifth. So therefore, no precipitate of calcium sulfate in this case.